is it the same at the two endpoints? Then this is the picture you would have, isn't it? Continuous function, closed interval, defined at the endpoints, same y coordinates at the end, right? The theorem says that there exists a number, c, in the interval AB. And notice, please, that it's in the interval. It's not at the endpoints. Within the interval, there is guaranteed a point such that the derivative is 0. Okay? So think about this. If I start at this point, and I have to end at this point, and they have to be the same heights, then it is impossible for me to draw from this point to this point with a continuous function without having some place where my slope of my tangent line is going to be 0. So like if I go up a little bit, I'm going to have to come back down, right? At some point. So if I go up, I'm going to have to come back down, which means there's going to be a place where the slope of the tangent line is 0. Yes? That's got to happen. We're guaranteed. Look at that. There's another example, right? That's a continuous function. The two endpoints are the same. You can go up and then go back down. Doesn't matter. Now you have two places, right? You actually have two places where the derivative is 0. Rolle's theorem guarantees us the existence of at least one. You could have a million in there. It's just you're guaranteed one. All right? What about this one? Straight line. So you're trying to get away with it there, right? You're trying to, I'll be sneaky, I'll just go straight across. They're all 0. The slope of the tangent line at every one of these points is 0. So you're good. You have at least one, right? Now, this last little statement here, you kind of lose it here, but isn't this 0 just the difference between these y coordinates? It's like take this y coordinate, subtract this y coordinate, you get 0, right? Okay, now that may not seem important now, but let's now move on. Can you all agree that Rolle's theorem makes perfect sense? Yes? You sure? Okay, now let's go to the mean value theorem. The mean value theorem says, where's my mouse? Come here. Where are you? Oh, it doesn't like this board. I want to make this a little bigger. The mean value theorem says, let f be a function such that f is continuous on AB. Same conditions of Rolle's theorem, right? Same condition. Next condition, f is differentiable on the inside. That's same as Rolle's, right? Now the third condition of Rolle's is that the endpoints have to be the same, right? There is no third condition here. So let's take a look at the picture and try and understand what's going on here. Get out of there. So with Rolle's theorem, these two endpoints do not have to be at the same height. All right? Did I say Rolle's theorem? Yeah. Mean value theorem, they do not have to be at the same height. What the mean value theorem says is that if you're going to get from here to here with the continuous function without picking up your pencil, then there's got to be somewhere in here, not where the slope of the tangent line is 0. No, that's not what this says. But it says where the slope of the tangent line is equal to the slope of that secant line. The line connecting these 2 points. Do you agree that this right here, this slope, whatever that is, that there's got to be somewhere in here where I'm equal to that, the same slope? Do you all see it? There's got to be somewhere where we have the same, this slope of the tangent line is equal to the slope of the secant line. Yes? Now I have something built in here. Let's see if I can't convince you. If you're not convinced of that, I can try to convince you by showing you that this is just Rolle's theorem rotated. That's all it is. It's Rolle's theorem rotated. So if you're okay with that, then you should be okay with that. Yes? Now, the reason why this right here the definition of that is this. So this is the slope of a secant line. It's the change, you can almost look at it like a little triangle here. What's your change in y? That's f of b minus f of a, right? And then this change in x is b minus a. So this dotted line, the slope of the dotted line is that. And we're saying that there's somewhere in here at C, somewhere, where the slope of the tangent line, which is the derivative, must be equal to the slope of the secant line. Okay, so let me try and recap that all in words again. If you have a continuous function on a closed interval a, b, then there must be some point within that interval where the slope of the tangent line is the same as the slope of the secant line connecting the two endpoints. Yes? All right. I have some more examples, so let's take a look at my other examples because I have no idea what they look like. Okay, so that one right there, if I bring in, you can see there, right? Yeah, this isn't very good. Okay, how about this? What if you have a straight line like that? Every point, right? Every point in there would work. All right, there's one more theorem, and then we're going to do some examples. That's it for mean value theorem. That's the theorem. We're going to do a couple examples. That's it. Okay, if the derivative is 0 for all x in some interval a, b, then f is a constant function on that interval. Do you agree with that? Like if I tell you, hey, look at this function between here and here, and I tell you the derivative is always 0 at every point, then it's got to be constant. All right, let's do an example. And then we're gonna have a little thinking game here, a classic debate, a problem that I really enjoy asking. All right, so let's do a problem where we can verify the mean value theorem. I think I'll make one up. Yeah. Okay. So verify the mean value theorem for f of x equals x squared minus 3x plus 1 on the interval -4, 6. So look what you're being asked to do. Verify. That means you need to show what's true. What does the mean value theorem say? So I'll put it up here so we have it. The mean value theorem says that there exists a C in the interval a, b such that the derivative of the function at C is equal to the slope of the secant line connecting the two endpoints, which is f of b minus f of a over b minus a. This is the mean value theorem. So we need to verify it, which means we need to find any value of C that would make this true. Understand? So I'm going to be working with this as an equality, working both sides of it, trying to figure out when do I get equality. So let's start with the left-hand side. What is the derivative of the function at C? So I'm going to start this out. Oh, I didn't ask. Is this continuous on a closed interval? Yes. Okay, so mean value theorem holds? Okay, so take derivative of this, and I'm going to do it with respect to C because that's the way it is in the formula, right? So it'll be 2C minus 3. That's the derivative of the left. That's the derivative of the function replacing x with C. All right, right-hand side. I'm going to do f of 6 minus f of -4 over 6 minus -4. Do y'all agree that's just me plugging in A, B? These are your endpoints A and B here. All right, let's plug and chug into that right-hand side, see what happens. 2c minus 3 equals f of 6. 36 minus 18, 19, I believe. 19 minus f of negative 4. 16 plus 12. 29? Come on, help me out, y'all. 29 over 10. Just double check my arithmetic there. 6 into here, right? 6 into here is 36. Take away 18 is 18, then plus 1 is 9, right? And then negative 4 into here, you get negative 4 squared is 16. Negative 3 times negative 4 is 12. 16 and 12 is 28, and then plus 1 is 29, okay? 29 over 10. Or 19 minus 29 over 10. So the right-hand side is negative 2.9? Oh, no. No. What? It's negative 1. What the hell am I doing? It's Monday. It's Monday squared. Okay, 19 minus 29 is still negative 10, and negative 10 divided by 10 is still negative 1. All right, add 3 to both sides. You get 2c is 2, and c is 1. Look, I made up this problem. The fact that this came out to be a nice integer was just random luck, okay? The fact that this is not a decimal is pretty amazing. Like, I didn't mean for that to happen. I would expect decimals as answers when you do your work. All right? So C is, no, that was pure just random chance. Pure random chance. Okay. All right. So what is this saying? Saying if I graph this, right? And I look at it just between negative 4 and 6, that if I go to the x value of 1, which we're calling the c value, and go to that point on the graph, the slope of the tangent line there should be equal to the slope of the secant line. I think that's worth looking at. Right? Did we successfully find that point? I mean, we did all the algebra right, I think. Let's see if this is working for me here. All right. So I'm going to be looking at x squared minus 3x plus 1. And I'm only going to be looking at that between negative 4 and 6. I'm going to have to zoom out. I'm going to have to zoom out so I can really kind of see it. All right, that should be good. I mean, it was a parabola, right? So it looks like at negative 4, I'm right about here, 29. And then at 6, I was right here at 19. And so if we connect these two, that line has a slope, right? Then if I go to, we got C was 1, right? If I go to 1, and I go get the slope of the tangent line right here, the slope of that tangent line, well, it'd be easier if I were further back. But those two lines should have the same slope, right? You believe it? I mean, if we would have got like C is 4, we'd be like, oh, we messed up, right? Because the slope would be like this, and that's not parallel. So these two are parallel, right? Okay. Why do they call this the mean value theorem? Mean, when we say mean, we don't mean like all pissed off mean, right? Like we mean average. So when you look at this right here, this part right here, this is your average value. This is your average, because I think it's easier to see it if you look at it in terms of quantities that make more sense. I'll do it this way. Let's say you have number of markers sold. Let's say this is your profit. Okay, so let's say 200 to 500. Let's say at 200 markers sold, you made $1,000. And then at 500 markers sold, these are very expensive markers. Let's say you made $3,000. Okay, let's just say, all right? Let's just say. Then what is the average between 200 and 500, what is your average profit per marker? How much are you making per marker? So what you would do is you would figure out, well, how much profit did I make between here and here? $2,000? And then how many markers did I sell? 300, right? So if I take 2,000 divide by 300, I get my profit per marker. Let's make this easier. Let's make that a 4, okay? Make that 2. So how much did I make per marker there? 10 bucks? So 2,000 over 200, I made $10, that's $1, $10 per marker, right? That was your average on that interval. The mean value theorem says there's somewhere in here, doesn't matter how your profits were looked in there, okay, it doesn't matter. Somewhere in there, you have a slope of a tangent line that is equivalent to your instantaneous rate of change, right? Your instantaneous rate of change has to be equal to your average rate of change. Yes? I have a better way of explaining it. That's visually what's happening. But let me do it this way. Let's say you're driving from home to school, right? And let's say when you're driving, it takes you 1 hour. We can keep the math simple. It takes you 1 hour to get here, and you went 40 miles. Exactly 40 miles to get to work or to get to school. It took you 1 hour. What was your average speed? What was your average speed? 40 miles per hour, right? So it looks like this. Time, distance. Let's say 40 minutes. 40 miles, right? Is what I said, 40 miles. And it took you 1 hour. Then you know that you started right here and you ended here. Now, were you driving 40 miles per hour the whole time? No, you're speeding up, slowing down, right? Okay, so your graph might look something like whatever, and you get here, right? What is the mean value theorem saying then? If your average speed was 40 miles per hour, then at some point you had to have gone 40 miles an hour. It's impossible to do an average speed of 40 miles per hour and not at some point be going 40 miles per hour. Does that make sense? So somewhere in here, right there at C, you were actually traveling your average speed. Okay? That's what the mean value theorem says. Yeah, that wasn't very good. So now the profound question. All this section is about on your homework is verify, verify. All right? There might be a few other kind of random problems in there, but my videos should kind of walk you through those. On your test, I will just ask you to verify the mean value theorem for something. But now we're going to have a profound question. And I love this question. We have 20 minutes to talk about it because it really gets people. I'm hoping people are going to start disagreeing, which is good. Okay, here we go. We all need to understand the question, so I'm going to draw it for us. We have two cars racing each other on a track. All right? So we're going to look from the top. Here's the starting line. And then here's the finishing line. And here's a car A. and car B. They are very awesome looking cars, yes. All right, so here's the scenario, right? 3, 2, 1, go. They both take off. They race. And at the end, it is a dead-on perfect tie. They tie at the end, okay? This is a theoretical problem, all right? So you have to, don't be talking about, well, it's impossible to tie, you know, all this stuff. Okay, this is a theoretical problem. 2 cars start, they race, and they come to the end of the track and they tie. So here's the question, and I want you to think about it. Is there a speed which both cars, is there a speed, sorry, in the race? I need to make sure you understand that in the race, which both cars must go or achieve, okay? Do you understand the question? Is there a speed somewhere within the race, all right? Is there a speed that they both have to go? Like, you have to go, that car A has to achieve that speed and car B has to achieve that speed. Is there a speed that they both have in common that they both have to achieve? So let's take a vote. How many of you believe that there is some speed that they both have to go that speed? Okay, what's the rationale behind that? It's what you just learned, right? Yeah. They both have the same starting point. So let me try and graph this. And I'm going to do this in color. Let's make car A blue. And let's make car B red. So do you agree that they both start here? Yes? And do you agree that at some point in time, I didn't tell you how long they were racing for, but at some point in time, that's the end of the race. That they're both at the same place at the end. So they're both here. Now we're assuming that these are continuous functions because the car is going to speed up and slow down. It doesn't like vanish off the surface of the earth and then come back and reappear, right? Like the car is going to be there the whole time, right? So they should both have some paths here. So the blue one does something and gets here. The red one does something. Maybe it overtakes and then whatever, right? What we just learned is that the mean value theorem guarantees us the existence of a point, like for the blue one, right? There is a point in here where the slope of the tangent line must be equal to the slope of the secant line, right? And the red one has the same thing. There exists some c for the red one that the slope of the tangent line must be equal to the slope of the secant line. But they both have the same secant line, yes? They both have the same secant line, which means they both qualify to have a c in there. Agreed? So there is a speed that they both must go, their average speed. I think we can almost unanimously agree on that. That's not the profound question. Here's the profound question. So can we answer yes here? Does it happen at the same time? Same time. Okay, I want you to think about that. Do you understand the question? We all agreed that they both have to achieve their average speed at some point in time, right? They both have to achieve their average speed, and they both have the same average speed. So there is some speed on the speedometer that both cars are going to see that speed at some point in time. My question is that point in time where they look at their speedometers the same for both cars? Are they saying this? So think about it. I'm going to step out for just a second and let you think about it. And then I'm going to come back and vote. And whoever's wrong is going to be dropped from the class. No, I'm just kidding. I just want people to be able to argue their case. All right? So you can try and argue. something to this. I'm not talking about at the beginning and at the end of the race. Because at the beginning, they're both going the same speed because they're stopped. And at the end, they're tied, coming across the finish line, they're going the same speed. Those don't count. Somewhere in the race. We have a couple more. How many of you have already formed your opinion? Everyone? Does anyone need more time to think about what their opinion is? So everyone's ready to vote? Okay. How many of you think that it does not have to happen at the same time? Okay. How many of you weren't going to change your mind? No. Okay. How many of you think it must happen at the same time? One? Okay. So let's hear some arguments. I'll wait on you since you're the only one. Any arguments as to why it does not have to happen at the same time? Anyone want to verbalize their case? Go ahead.
Because their average speed,
Mm-hmm.
it doesn't have to be in the middle, I guess. It can be at an end, and then one can be at the beginning, that they reach their average speed, and then it can just be inconsistent the whole way.
Yeah, so like maybe in the beginning one of them goes fast, the other one goes slow. Mm-hmm. And so the one in the beginning hits his average speed earlier, the other one hits it later. That's a decent argument. Anyone want to support that argument? So that argument is done. Should we settle it or no? Anyone else want to add some more oomph to that? We're good? Does everyone understand the argument? Let me try and, can I try and draw your argument? Can I try and draw your argument for you? Let's see. So let's say blue car does something like this. And let's say red car does something like this. Right? Then this blue curve, this steeper tangent lines mean faster, right? And then less steep, slower. So this one's going fast in the beginning, slows down. This one is slow in the beginning, speeds up. You're saying that this guy's going to reach his average speed earlier than this one. Okay, so it's not guaranteed. Maybe it could happen, but it's not guaranteed, right? Do you want to try and argue?
My logic was just that's a little too obvious, and if it's a profound question, then it's got to be...
Good. So you went with he has to be asking this for a reason, yes.
Well, you could also say because they crossed the finish line at the same time, they had to be lined up in order to cross at the same time. So at that time when they were both lined up, they had to be going the same speed. Potentially.
What do y'all think about that?
Because if one was going faster than the other, they wouldn't have crossed at the same time.
That was at the end points. You said that at the end points, right?
No, he's not suggesting the end points. He's saying because they're tied at the end, one of them had to pass the other at some point, right? To meet up.
Maybe they both were going the same speed the whole time.
Okay, so if they go the same speed the whole time, right, then this problem is, the answer is yes. But what this question is saying is regardless of how they do it, if they start together, end together, is there a time where they're both going the same speed at the same instant? Is it guaranteed? Is it guaranteed for any race that starts as a tie and ends as a tie that there's some point in the race where they're both going the same speed, the exact same moment? So the answer, of course, because it is profound, is yes, it is guaranteed. There is a moment in time where they both must be going the same speed at that same moment. The reason why I think this is a profound question is because you saw the overwhelming majority of intuition that tells you that no, it's not guaranteed, right? Right? I mean, did we have an overwhelming majority? Okay, this is one of those cases where intuition is not going to serve you well here, and we have to depend on the mathematics to be able to get to the answer. So a lot of times you say, go with your gut, go with your intuition. If you're building a bridge, you can't just be like, yeah, it looks tough enough, that looks strong enough, right? We saw that bridge collapse in Florida, right? I'm not saying that was, anything like this, but Look, intuition is trumped by mathematics, all right? Always. Always. So let me prove it to you. I can prove it to you. It's pretty easy to prove, all right? You just have to follow it. Okay, so let's take this scenario right here, because this scenario right here is very general, right? It's a very general, someone else could draw the picture a different way, but I'm going to rely on a lot of different things here, so let's see if you can follow this. This is kind of an abstract sort of proof. Let's call the blue function B of t for blue car, the blue's position with respect to time, and let's call the red car R of t, the red car's position with respect to time. With me? I'm going to generate a new function from these two functions. The new function I'm going to create is, I'm just going to call it capital D of t. It's a new function, and what it is B of t minus R of t, which is just the difference of their positions. All right? Let's call the time when they start A, even though we know that's 0, and let's call the time that they stop B. Is that okay? This new function D is continuous. Right? Is a continuous function? Why is it continuous? Well, the blue car is a continuous path, right? The red car is a continuous path, and therefore the difference between two continuous functions is still continuous. So do you agree that capital D of t is a continuous function on the interval? All right. Capital D is differentiable on the inside of AB. Oh, I should have put is continuous on AB. So it's continuous, obviously, because the interval I'm looking at is AB. So it's differentiable. It's differentiable because these curves don't have cusps or corners. And that's because you can't be driving and you're doing 20 miles an hour and then in the next instant you're going 30, right? It has to smoothly, gradually change, right? It's not like instantaneous warp speed. So these are differentiable because they're nice and smooth. All right. What is D of A? Oh, well, no, let me do this. Let me do this. The mean value theorem says there exists a point C in AB, right? In AB, not the closed interval, inside the open interval here, such that what? What does mean value theorem say about this capital D? The derivative at C, right, is equal to the slope of the tangent line, slope of the secant line, which would be capital D of B minus capital D of A over B minus A. Do you all follow this? You sure? Does anybody know what this right side is? What's capital D of B minus capital D of A? Look at this function. This function is the difference between their positions, right? It's measuring this, capital D is measuring these distances between here, right? So in the beginning, capital D is positive, right? Because B is bigger than R. And then capital D right here. What's capital D right here at that point? 0, because the difference is 0, right? Between their positions. So what is capital D of B? What's the difference between their positions at the end? 0. What's the difference of their positions at the beginning? 0. And then B minus A is a number, right? But who cares? The right side is 0. Do you agree? Yeah. Okay. So what this says is that capital D of C is 0. Somewhere in here, the slope of the tangent line of this capital D is 0. Agreed? Mm-hmm. Okay, but what is the left-hand side? What is the derivative of capital D? So just go up here. How would I take the derivative of this? How would I take derivative? I take derivative here, I get capital D prime of t is equal to, how do you take derivative over here? Just one by one, right? What's the derivative of this? B prime of t What's the derivative of this? R prime of t. So what we're saying is this. Because I came up with this difference function, it's continuous, it's differentiable, mean value theorem says there's a point in there where the derivative happens to be 0, right? But if I replace the left-hand side with its definition, doesn't that mean that b prime of c minus r prime of c has to be 0? Yes? Okay, move this over. And what is this saying? There's a point C in the interval AB where the derivative of B is equal to the derivative of R, which means that the speed of this car is exactly the same as this car at the same point in time. That's the proof. I mean, if you followed that, great. If you didn't, it's okay too. But this goes to show you how your intuition can work against you, all right? But it relies on the mean value theorem. You have to have that theorem in order to be able to prove that. So it does go back to that, let's take that scenario where the two cars are racing. Let's try and see where it happens. It's going to be hard, but let's try it. Okay, so if we start moving these, they go together and this one speeds up, right? Then, ready, go like that. Then you could argue, I think that was the argument right there, that where they wouldn't have reached, right? So it's like this, goes off like that, and then they meet like this, right? What's lost in that is that's impossible because I'm controlling the markers, right? And they both have to go the same average speed. So I don't get the freedom to move these as much. What's dictating is they both have to go the same average speed. It's tough. This is a hard argument because I think that's a great picture of the argument against. This one's going faster, and then they tie, right? So they tied it. They were going the same speed at the end and the beginning, but it's hard to see it. I hope the proof was enough for you, though. Maybe not. Okay, let's do this. I want to give everyone credit for being here today because it was a holiday, and obviously some people took an extended holiday. So I'll just call your name real quick. Nicholas.
Here.
Once I call you, you may go. And I'm going to turn my camera off. Or actually, I'll just mute it.